Okay, so in this video, we're going to carry on with our impulse and momentum, and we're going to look at Newton's experimental law, which is our coefficient of restitution. Okay, but we're going to obviously now look at it with vectors and how it affects. Okay, so in terms of my coefficient restitution, okay, we have our equation from FMU6, okay, which is at E, which is our speed of separation over our speed of approach. Okay, now when we had two particles just collided straight on like we did before, okay, it was nice and easy to figure out what my approach is and what my separation was and things like that, okay? But however, we're going to have some vectors involved now. Now, we're going to look at two different scenarios, okay? The first one, which is this video, is going to be impact with a plane, okay? So that's like with the floor or with a vertical wall like this. And the other one is when we're going to have two particles but they're coming in at each other at different angles. Okay, so for example, I can have them moving like this. Okay, and they're going to collide eventually. Okay, so those are two different scenarios we're going to look at. Okay, now the first one, slightly easier. Okay, but we do need to consider certain things. Okay, so let's consider these two blocks here. Okay, I've got this initial velocity, so it's moving towards the wall, and then this is final velocity where it's moving away from the wall, so it bounces off. Okay, now if it's a smooth wall and it's perfectly symmetrical, this angle here should be the same as this angle here. Okay, it should bounce off at the same angle it hits at. Okay, but sometimes there's different scenarios in which that doesn't happen, so just be careful of the question. Okay, now what's important is that only one direction is going to change. Okay, so in this scenario, when it hits a vertical wall, okay, my vertical velocity isn't going to change, okay, because that's not where the impulse is taking place. Okay, so my vertical component of my velocities are going to stay the same. Okay, the bit that's going to change is my x components, my horizontal components. Okay, and they're going to change depending on my thing. Because if we think about what's happening, I'm approaching at U1, that's my x. Okay, and I'm separating at V1. That's how far I'm moving away from the wall, and how closely and how fast I'm coming into the wall. Okay, how fast I'm going up and down isn't really affecting how close I'm getting towards the wall and coming away from the wall. Okay, so in other words, this generally simplifies to this equation here. Okay, so I've got V1 over U1. Okay, so it can be a little bit easier for us to work with. Okay, and then we've got a path about the impulse, smooth plane. Once particles in contact with the plane, there's a reaction with the plane. Okay, so it's perpendicular. Okay, it's normal kind of thinking. We can also link our impulse into this kind of question. Okay, so this is a scenario that we're going to look at for the first example. So just like before, let's get some diagrams drawn and get ready to go on this one. So we've got a smooth particle of mass 2 kilograms. Okay, strikes a smooth fixed wall. Its velocity before its impact is 5 meters a second at an angle of 30. Okay, to the normal of the wall. If the coefficient of restitution, so it tells me E is 0.6, that's my E. Find the following. So I want the velocity particle after it hits the wall, the impact, the impulse, and then the loss of kinetic energy. So first of all, let's draw some diagrams. I firstly got it's coming up. It's going to hit the wall at 5 meters a second. Okay, and it's 30 degrees to the normal. So this is the normal here, this dotted line. So it's going to be 30 degrees, is going to be here. Okay, then it's going to have, when it's at the wall, it's going to have its impulse. And then after it's hit it, it's going to bounce off with some sort of velocity. Okay, so what we're going to do is we're going to firstly split this one into its components. So U, okay, is going to be 5 cos 30 is going to be its x component, and 5 sine 30 is going to be its y component. Okay, J finds is V. I don't know what it is yet, and actually it's what I want to find in the first question. So I'm just going to define it as, let's think, it's going to the left, so it's going to be a negative. So I'm going to have a negative something to the left, and then I'm going to have Q, let's call it P and Q. Okay, I call it A and B, I can call it whatever I want, I'm just going to go with P and Q. Okay. So for part one, I need to find the velocity. Okay. So what I'm going to apply is I'm going to think of, well, I know what E is. I know E is 0.6. Okay, now I also should know that this is the speed of separation over the speed of approach. Okay, so my speed of separation in this case is just going to be the x components. Okay, so speed of separation is just going to be p in this case, and my speed of approach is going to be 5 cos 30. Okay, so I've now got, if I solve this, I've got p is 3 cos 30. Okay, and then I can use the fact that there's no impulse in the y direction, so my y component is going to stay the same. So q is simply going to be 5 sine 30, and I'm going to state y. Okay, there's no impulse in y direction. Okay, so therefore I can do my v. Therefore, v is going to equal minus 3 cos 30. And then 5 sine 30. Now, realistically, those are probably going to give me some quite nice straight out. I'm just going to leave them as sine and coses for this instant. Okay, and there's my answer for the first one. Okay, so now for part B, I want the impulse. So straight away, impulse J is my change in momentum. Now let's remember, we got to take a certain direction, okay, as positive, okay, for an impulse. So it doesn't matter which way I take it as positive, okay. What's nice about vectors is that they're already in terms of a direction, okay. So when I plug this in, I'm just going to have the change in momentum, okay. So it's final momentum take away its initial, so I'm going to have 2, and its final momentum was minus 3 cos 30, 5 sine 30. And then its initial momentum is 2, and then 5 cos 30, 5 sine 30. Okay, and I'm going to solve this. Okay, now x components, I'm just going to plug in my calculator, gives me minus 13.86. Okay, and then my y components, if I plug it into my calculator, gives me 0, which is what it should be. Let's remember, okay, I should only have it working like it does up here in the x direction. Okay, and I've got a negative because kind of like our normal set of axes, okay, x, y. Okay, this is going to have the j's working in negative x, which is why I got a minus 13.86, so it makes sense for me to get a negative out. Okay, last one, C, is my loss in Ke. Okay, that's going to be its initial Ke, take away its final Ke. So its initial Ke, nice and easy, is going to be a half times 2 times 5 squared. Okay, I can use the 5 in this case from here. Okay, I could technically use Pythag on my vector, but it's just going to give me 5 anyway. Okay, and then I'm going to take away its final, which is going to be a half times 2 times by, and then I need to use some Pythag on this. Okay, so I'm going to do the root of 3 cos 30 all squared. Okay, let me zoom out a little bit. And then I'm going to plus 5 sine 30 squared. I'm square rooted. That's going to give me the length, and I'm going to square it again. Now we know that that square and square root are going to cancel each other out. Okay, but we'll write them in just to like prove the point of what I'm doing. Okay, gives me 12 joules. So I'm going to lose 12 joules of kinetic energy. Okay, so key bits. Okay, let's make sure we draw nice clear diagrams if it's hitting the wall. In a similar kind of manner, we could have, let me just scroll down very quickly, a floor, and it comes at the floor and then bounces off the floor, which means J is only working in the y direction. Okay, which would just flip things around. It means my x components would stay the same, and then my y components would be what's changing with the impulse. Okay, so be careful of what the question is. If it's hitting a vertical wall, my verticals stay the same. If it's in a horizontal floor, my horizontals stay the same. Okay, right. But apart from that, okay, the next video, okay, we're going to go over a question where we've got a collision between two spheres. Okay, so apart from that, I'll see you in the next video.